For decades, automotive safety was defined by the physical durability of brakes and steering racks. Today, vehicles rely on the invisible field of an artificial intelligence perception module to navigate through these shadows. This transition to software-defined vehicles introduces a specific engineering friction. With a fixed mechanical response, an AI perception system assigns varying statistical weights to every object it detects. It is essentially making a series of highly educated guesses about the road ahead. Because mechanical safety standards are designed to verify binary failures, they lack the mathematical tools to certify a system that operates on a sliding scale of probability. This incompatibility requires a new technical framework. To build that framework, we have to look at how these systems are tested. In a standard 1,000-kilometer drive, a pedestrian might occupy the vehicle's path for less than 1% of the total distance. This creates the accuracy paradox. An AI predicting empty road constantly matches the environment for 990 kilometers, generating 99% accuracy. This massive majority class statistically swallows the minority failure. The model looks exceptional, despite missing a human being. ISO.PAS 8800 provides the engineering mandate to dismantle these misleading aggregate metrics. It replaces them with granular, testable safety proofs that isolate the minority class. A 99% accuracy score provides zero safety value if the remaining 1% error margin results in a fatal collision. For an automatic emergency braking, or AEB system, the absolute physical safety requirement is exactly 0 pedestrian collisions on the road. To reach that requirement, ISO.PAS 8800 utilizes the confusion matrix. This tool categorizes every prediction into 4 distinct quadrants, mapping abstract statistics to physical vehicle behaviors. False negatives represent the most critical risk. The system identifies a real pedestrian as empty space and fails to engage the brakes. False positives occur when the AI hallucinations an obstacle. This triggers phantom braking, which can lead to rear-end collisions from following traffic. True negatives represent the vast stretches of empty road. This is the quadrant responsible for the statistical inflation of simple accuracy scores. By deconstructing performance into these 4 types, engineers can identify exactly which type of error is most likely to cause a physical crash. These error types are in constant tension. Improving recall to catch every pedestrian almost always lowers precision, making the car more likely to brake for shadows or trash. In safety-critical AEB systems, engineers must prioritize recall, pushing it toward 1.0 to ensure no pedestrian is ever ignored. However, forcing recall this high can make a vehicle unusable on public roads, as it slams on the brakes for non-existent threats. To evaluate the relationship between these two, the standard mandates the F1 score. This chart compares a standard arithmetic mean against the harmonic mean used for the F1 score. The harmonic mean is used because it is sensitive to extreme disparities. If a model has high precision but fails nearly all its recall tests, the F1 calculation drags the score down to roughly 0.18, signaling a failure. This prevents an AI from being certified if it hides a single catastrophic blind spot behind an otherwise high mathematical average. Detection alone is insufficient for safety. The vehicle must identify the pedestrian's exact physical coordinates to calculate the necessary braking distance. We use intersection over union, or IOU, to measure this. It calculates the degree of overlap between where the AI thinks the pedestrian is and where they actually are. When we raise the required IOU from 0.5 to a strict 0.95, the visual success rate drops. This reveals small coordinate errors that could lead to miscalculated stopping distances. ISO.PAS 8800 requires testing MAP, or mean average precision, across these strict spatial tolerances to ensure the AI's positioning is physically reliable. Validating this coordinate precision mathematically locks the AI's spatial awareness to the tight physical tolerances required for a safe, controlled braking maneuver. Beyond identification, the system must continuously predict values like closing velocity and the exact distance to the obstacle. In these regression tasks, engineers distinguish between minor sensor noise and the catastrophic miscalculations that lead to impact. We compare mean absolute error, which penalizes a 10-meter deviation linearly, against mean squared error, which applies a massive squared area penalty to that same mistake. Mean squared error is the preferred safety metric because it geometrically punishes large deviations, forcing the model to prioritize the elimination of extreme outliers. In the physics of a moving vehicle, a single 10-meter error is far more lethal than 10 1-meter errors. The math is designed to reflect that physical reality. These metrics only hold weight if the underlying test data is rigorous. The standard requires a data V model, ensuring the dataset includes rare edge cases and represents actual environmental factors like fog, rain, or glare. Without representative data, engineers can fall into the AUC Trap, a common pitfall in autonomous driving evaluation. Because the AUROC curve calculates false positive rate against the vast volume of empty roads, the horizontal axis compresses, making the curve look artificially perfect. ISO.PAS 8800 mandates cross-referencing precision recall curves. This removes the statistical padding, exposing the AI's true performance when pedestrians are present. A mathematically perfect score is a lethal illusion if it was generated using non-representative data or misleading charts. We have moved from a simple 99% accuracy score to a multi-layered matrix of precision-punishing metrics. In safety-critical systems, these formulas provide the direct mathematical link to life-and-death physical outcomes. Under ISO.PAS 8800, machine learning evaluation functions as a search for hidden risks rather than a quest for a passing grade. These metrics, F1, MAP, and MSE, interlock to form a safety envelope around the vehicle. Only when an AI's behavior is mathematically constrained within this rigorous envelope can it be trusted as a partner on public roads.